Hello class, and thank you for watching this video on 3.7. In this first part of inverse functions, we're going to discuss the definition, what an inverse does. We're going to use that definition to find the inverse using tables and graphs, and also evaluate the inverse of a function using the table, using the graph, and using an equation as well. So let's begin with what an inverse is. Now, an inverse function is going to undo any given relation. Every inverse function can be found by simply switching the input and output value. Okay. Now, in some cases, this process is really intuitive. So we can see that if a relation is multiplying my input values by x, intuitively we can think, well, if we're multiplying by 3, then the opposite of that, the inverse, to undo that operation, we would divide by 3. So sometimes it's a little obvious and intuitive to figure that out. Other times it's not that obvious. But regardless of the case, it's important that we understand the main concept of what an inverse does, which is, again, switching, which is represented in this diagram. So if I make the x values the y values and the y values the x values for the inverse, for a function, I can create the inverse of that relation, and the result of that rule, whatever the formula is or the equation for that thing, hopefully it's a function itself, can be represented with that value there, with that scenario, with that situation. So let's consider this part right here. So we have example 1 right here. Let's find the inverse of this function given this table. So again, the main concept of identifying an inverse is to simply switch the input and output values. So since my input values to my relation are 1, 3, 4, and 6, and the output values are negative 1, 2, 0, and 2, by switching those, the new input values would be negative 1, positive 2, 0, and 2, and the new output values would be 1, 3, 4, and 6. So using a regression, using again some way of figuring out what this formula looks like, I can possibly graph it and see what the relation will look like, giving me an idea what type of function I have there, if in case I do have a function. Now, if you note and pay very close attention to the table that we have here on the right, again, this right here, this relation represents an actual function because all my input values are not repeating. It has every single one of my x values has only one y value. So this does represent a function because, like I said, each x value has exactly one y value. So we have that equal correspondence. Every x has only one y. However, if you look at the inverse that we created over here, this is the inverse. This is not a function because every x value does not have a different unique y value. 2 has an output value of 3, and this 2 has an output value of 6. So this is not a function because 2 has 2 different outputs, 3 and 6. So sometimes when we have a function and we get the inverse, it doesn't necessarily create a function as well, okay? But we can still figure out what the inverse relation is, even though we cannot classify it as a function. So let's take into account again this exact same idea with this graph right here. So like I mentioned, not every relation, the inverse of every relation is going to also create a function. Take into account again this graph that we see here. By the vertical line test, we see that this relation is a function. Again, it's only going to intersect the relation. Any vertical line that I draw only intersects the relation at one place. But if I look again at the points, and I get the inverse of this, which again, the main concept of finding the inverse is by simply switching the x and y values, I can graph this function and see what the, I can graph the inverse and see what the inverse looks like. So I'm going to put the points, those coordinate points, I'm going to put them over here at the bottom. So we have negative 2, negative 1. So the inverse of that would simply switch that to negative 1, negative 2. So let me plot that in blue. So negative 2, negative 1, negative 2, which would be right here. The point, this point up here is at negative 1, positive 2, negative 1, positive 2, and the inverse of that switches the order of that, so 2, negative 1. So 2, negative 1 right there. So let me connect those 2 points. Then we have this point here, which is at 2, 1. So 2, 1, the inverse of that would put it at 1, 2. So plotting that point at 1, 2, we'll put it right there. So let me connect that again with a straight line. And then our last point, which is this one all the way over here. So I could just make straight lines. It's at 4, 3. So the inverse of that again simply switches the order of those two, of that coordinate. So it's going to be at 3 and then 4. Okay, so that's what this line will look like. Now, if you'll notice this inverse, notice that this inverse is not a function. I can draw a vertical line here and touch this relation in multiple places, here and there. So again, not every inverse is also going to create a function of the original function itself or the original relation. And it could be also backwards. Maybe we have something that is not a function, but when we get the inverse, it does create a function. Now, the cool part about this, which is really, really amazing here, is that if you pay very close attention, notice that if I draw a diagonal line right here, going through the origin with a slope of 1, rising up 1 over 1, 1 over 1, which is the equation y equals positive x, y equals to x. So this diagonal line, y equals to x. Notice that because all we're doing is switching the order of our x and y value, y equals to x, you see y is first and x is second, we end up creating a reflection of our relation across this red line. So every inverse of said relation or function is always going to be a reflection of our inverse or our relation. Let me start over. I'm saying it all wrong. Every inverse is going to be a reflection of our function or our relation across this red line, across this equation of y equals x. So hopefully, again, I didn't confuse you with everything of my stuttering, and this is clear. So very, very, very cool, again, that we see this type of relationship between the inverse and the original function / relation of this thing. So it's a reflection across the line. So very, very cool how that works. So now if you'll please turn to the second page, and let's talk about, again, our main learning objective, which is how do we evaluate, now that we know how to create the inverse of a function, how do we use this information to evaluate and determine the value of a function for a specific x value? Well, first of all, let's talk about the notation. If f and g are inverses of each other, we can say that g is the inverse of f. And to denote that, we use the notation of f and simply put a -1 on the exponent of that f of x. And vice versa, if again f and g are inverses of each other, we can say that f of x is equal to the inverse of g. And again, the notation would simply be g with a -1 as an exponent of x. So this is the notation that we use to determine, or to indicate that we have an inverse of something. And of course, f could be the inverse of itself, or whatever the case is. So we just have that. So to indicate that we have an inverse of something, we simply add this little exponent, negative exponent, to our function. Now, this is not the same as your exponent rules. So do not confuse this with the following from your exponent rules, like x to the -1, how that equals to 1 over x. This is not true when it comes with functions. F inverse of that is not just simply the reciprocal of this, okay? Those are not going to be true. This only works for a variable, for a number, okay? This does not work for a function. So it's not the exact same thing, okay? And now second, because the main concept of finding the inverse is simply switching. If f of x is a point on the graph of f, then the inverse is going to simply flip the order of those two things. Y and x is going to be a point on the graph of the inverse. Remember, g of x is the inverse. So within inverse functions, all the x values and y values are switched. So graphical behaviors in terms of x and y are also switched, meaning that your domain is going to change to your range, and the values that are referred to as range are now going to become your domain. Okay, so let's take into account this example right here. So let f and h be continuous functions with selected values in the table, and let's find all the possible values for this. So here we have this table, and the first thing we're going to do is figure out what the inverse of the value of f is when x is equal to -3. Since the concept, again, is that the inverse simply switches the x and y value, let's use the table underneath to create a table of values for the inverse of f. So that, again, like I mentioned, that simply switches the x and y. So the x input values will be 6, 3, 1, -1, -3, and -7, while the output values will be -3, -2, 0, 1, 4, and 6. So you see, I made these the y values to the inverse, and the y values of the function became the input values of the inverse. So using this table here, I can evaluate and figure out what f inverse of -3 equals. And again, the way that we read this, we say f inverse of -3. So what is this going to equal to? Well, according to the table, when x is -3, on the inverse, the y value, the output value, is 4. Sorry, 4. So there is your answer. So the value of the inverse at -3 of f equals 4. Now we can also do this without having to switch, because again, the idea is that we're just simply switching the x and y. We can read this backwards. So from here, remember, this for the inverse, this is going to be the x value, and these values right here are going to be the output values to the inverse. So if I look at this and look at -3 on this table here, on this row, I see that the input value is 4. So another way of thinking about this is that if I look at the original function, what I'm trying to figure out is basically solving an equation. So I'm looking for where the function is going to have an output value of -3. So doing it like that, I see that the function f of x has an output value. This f of x equals to -3 when the x value is 4. So the solution to this equation, x equals to 4, is again the value to the inverse at this number -3. So again, all of this again correlates to itself, and it correlates again and it connects to itself in that idea and that aspect. So let's look at the next example. So the next example, the same thing. Figuring out what f inverse of 1 equals is the same thing as figuring out when is the function going to equal to +1. So let's first look at, let's do this first using the table down here. And let's look at what the x value is when 1 for the inverse and what the output value. So the output value is 0. So f inverse of 1 equals 0. That right there is going to be your answer. And look at the solution to this equation that I have right here on the right. What value of x is going to give me an output value of 1? So looking at the table for f of x equals to +1 when the x value is 0. And notice again, those are the same numbers we're looking for. So the solution to this equation is the same value for the inverse at this number of 1. So let's look at the next example. Here we have the table for h. So we want to get the inverse of h and figure out what does h inverse of -3 equals. So h inverse of -3 equals. Now remember that figuring this out is the same thing as solving the equation when does h of x equal to this output value of -3. So let's first do it that way using this table without flipping anything. So here's h of x. We want to know when h of x equals -3. So according to the table, h of x equals -3 when the input value of x is 1. So the solution to this equation is x equals 1. So now, let's see if it matches when I get the inverse here. So to create the inverse of h, we're simply going to switch the x and y values. And we see that, yep, when x is -3, the output value is 1. So h of x at -3 equals to the value of 1. So like I mentioned again, the solution to that equation is the solution to the inverse of h at that number. So similarly, we can do the same thing here. So here, we're just looking for the input value at 1. Since we already have the table there, let me just ignore that, ignore this. So h of x equals to 1 when the output value is when the input value is -3. So here, x would have to equal to -3 to solve this equation. So that means h of 1 equals -3. So there is your solution. So moving along, let's apply this again to something that we talked about earlier, compositions. So using now compositions, let's use what we learned about composition in order to evaluate the composition of inverse with something else. So here, we want to do and determine the value of h inverse of f of what? So to do this, recall that the first step is that we work from inside the composition. So I first want to do and evaluate this. So I want to determine what does f of 1 equal. So from our table, again, here's the f table. When x is equal to +1, the y value is -1. So f of +1 equals -1. So we have that number there. Now, because it's a composition, that solution, since this equals -1, we're now going to evaluate h at that output value of -1. So the input value to the inverse of h is going to be that answer that we got from the first part. So step 2 is now to evaluate h at -1. So the inverse of h at -1. So let's use the table for the inverse right here. And let's look at when x is -1, the y value is -2. Or you could have done it the other way. Remember, this is the same thing as determining when does h of x equal -1. So without creating this table here, we can look when does h of x equal -1. Well, the output is -2, which is again the same thing that we got earlier. So the value of the inverse at -1 of h is -2, so there's your answer. So your answer here is that h inverse of f of 1 is -2. So let's now look at the next example. So in the next example, we want to evaluate this. So we're going to begin again by first evaluating the inside right there, which is the inverse of f at 3. So the inverse of f at 3, well, that means again that we're trying to determine when does f of x equal 3. But since we already have the table for the inverse of f, let's just look at that. So we're going to input 3. So using this table, when x is 3, the y value is -2. So f inverse of 3 equals 2. +2, right? No, -2. I want to get that right. So now that we have that, now that we know that that's 2, we can now evaluate h at that input value. So step 1, working with the inside, gives us an output of -2. And step 2 is to using that output, plug that in as the input to the outer function h. So going to the table for h, and looking at the x value of -2, we see that the y value is -1. So our output value is -1. And there's your answer. So h of f inverse of +3 equals -1. Okay, let's now move on to the next page. So how do we do this with graphs? Well, with graphs, again, recall what I mentioned earlier, that a graph is simply a reflection of this function here. The inverse is going to be a reflection of this function across the line y equals x which again is simply going to flip all the x and y values. So let me graph this, the inverse in blue. So starting off with this point here, which is at -4 for x and -3 for y, that's going to flip to -3, -3, -4. So that's going to put that point right there. You see how it's a reflection across that red line. Then you doing this one just to make a straight line. I'm going to use this point and then this point to connect in a straight line. This point is at 4, -1, so the inverse of that would be -4, +1. -4, I'm sorry, -1, +4. And then just continuing. So that point now, since this point connects to this, let's get the inverse of this coordinate. 6, 4 will be 4, 6. And then lastly, this point here, 11, 6 would be 6 and 11. So it's going to be out there. So I'm not going to plot that point, but it'll be out all the way out there. But just looking at these points there, this point, and this point, we can see again that it's been reflected across this red line of y equals x. So let's use this blue graph there, the inverse of k, to evaluate k inverse at 4 and at -1. So k inverse of 4 according to the graph, and for x is 4. And we're not looking at this point there, we're looking at the y value of the inverse, which is the blue one. We see that the y value is 6. So your answer is 6. And the inverse of k when x is -1. So looking along the x-axis at -1, the output value, again, is not this one down there, it's on this here, is going to be +4. So there is your value to the inverse at those specific values for k. Well, k inverse, not k, but k inverse, the inverse of k. Now another strategy for this is that instead of graphing again the inverse and drawing a reflection of this graph across the equation y is equal to x, remember, all we're doing is just switching all of the x's and all the y's. So another simple trick or another technique we can do is that change the labels on the domain and the range. So for the function f of x, this is your domain x and this is your range, your y's. For the inverse, those are going to switch. So if I just simply change this to label to my x and change this label as my y, I don't have to graph the inverse of this. I can just simply look at this graph inverted. So if I want to figure out the inverse of f at -3, instead of looking at this horizontal line at -3, which is the x value for f, the x value of the inverse will be through here. So if I look at -3 here, I see that the y value is going to be 8. This again correlates to the idea that I'm simply solving an equation. Finding this number here is finding the solution to the equation. When does f of x equal to -3? Which again, the solution to that is 8. But another, like I said, this nice strategy here is just simply, again, inverting the domain and the range, because that's what we're going to do. When we graph the inverse, we're just going to invert the domain and the range, and the image is going to be a reflection of this thing across the line y equals x. But if I just do this, this does, again, the same thing. So the value of the inverse of f at 1 gives us again the ability of doing that. So if I read this as my input value of 1, I see that the output value is 3. Which sometimes makes it easier again to see that, because if I only focus on graphing the inverse using again these points here, because I don't want to do too many points, I create segments and I miss out points that are in between, like these points right there, or these points right there. So this technique again just gives me a different alternative and a different method to getting the inverse values of a function, or to evaluate the inverse of a function by just simply switching the domain and the range in the graph itself and reading it again backwards, which, like I said, is essentially just figuring out the equation, the solution to an equation using a graph to first -3 and f of x. When is that going to equal to 1? And the solution to this equation is 8, and this right here would have to be 3. And now this finally takes us to the last set of examples. How do we do this with equations? Well, again, since we're simply switching the x and y values, remember, f of x is just a fancy way of writing y. So y equals, let me zoom in here, y equals to 3x minus 7. And since the inverse is going to switch the x and the y, the inverse of this will give us the equation x equals to 3y minus 7. And since the objective here is to plug in 20 into the inverse, so here's my inverse, plugging in 20 in here will give us the equation 20 equals to 3y minus 7, which is the same thing as 3y minus 7 equals 20. And well, to solve this equation here, because it's a linear equation, we just simply do letters to the left and numbers to the right. But before we go into that, look again what I simply did. I simply got my function and replaced the y with, again, 20. So I just simply get this and I set it equal to 20. Because evaluating the inverse at a specific number is the exact same thing, and I'll write this down here, 5 inverse of 20 is the exact same question as figuring out this equation. When is f of x going to equal to 20? And that's exactly what we did. Notice f of x, again, 3x minus 7 is f of x. F of x equals to this value of 20. So now let's go into how to solve this. Well, because it's a linear equation, the technique is pretty simple. We're going to move this 7 to this side, making it positive 7. So 3x equals 27. Dividing both sides by 3, we get that x equals 9. So there's our answer. So the value of the inverse of f at 20 is 9. So there is your answer. So let's move on to the next example. So for this example right here, again, the idea is the same. So since f of x is now defined as 3 times the square root of x minus 7, to find the value of the inverse of f at -1, that's the same question as determining when does f of x equal -1. So we're going to simply set up an equation. So the 3 times the square root of x minus 7 is going to be set to that value of -1. So again, see, we're switching the x and the y. So here, the way to solve this equation would start the same way. We would start by moving the 7 to the other side, making it positive 7. So 3 times the square root of x equals 6. We'll divide yet again by 3. And the square root of x equals 2. Now the last one, this is where we stop, but because we have the square root, to get rid of the square roots, we use the inverse operations to squares, which is, like I mentioned, squares are the inverse operations to square roots. So we get that the solution here is x equals 4. Let me move this over. Sorry. Didn't make this box big enough. Let me move this over. So here's our answer. So the f inverse of -1 equals to a total of 4. Now the remaining two examples are set up the exact same way, but I want to go over again the solving part. How do we solve it when it's x to the third and the cube root of x in those situations, okay? So to find the value of the inverse of f at 17, we would get our function f of x, we would get our function f of x and set it equal to 17. So here, like I mentioned, that would be 3 times x to the third power minus 7 equals 17. So we would start again the same way, move its constants. So plus 7 to both sides. Three x to the third power equals 24. We're going to divide by 3. X to the third power equals 8. And then here, the opposite of raising something to the third power is using a root, using the cube root. So let me move this over. And we're going to take the cube root of this side as well. So you see, the same steps again are the same as before. Had I used different numbers, the procedure will still be the same. Moving this over and then dividing by that. Moving this over, dividing by that. So if you could do one, you could do an infinite examples of these because the procedure is going to be the same. You want to isolate again our x. From there, depending on whether we have a power or we have a root, we'll determine if we have an extra step. So here, this last step was to get rid of the power of 3, which would be the cube root of x to the third. And doing the same thing on the right side, the cube root of 8. That equals to 2. So your answer is positive 2. And our last example will be set up by taking 3 times, this is the cube root of x minus 7, and we're going to set that equal to 2. So solving this equation, we'll again move the 7 to this side, making it positive 7. So 3 times the cube root of x equals 9. We'll divide both sides by 3. And the 3 that's going to be divided out is this 3 right there. So the cube root of x equals positive 3. And the inverse of a cube root is a power. So powers use roots to cancel out, and roots use powers to cancel out. So here we're going to raise both sides to the power of 3. I think might have said the same thing twice. So we use powers to get rid of roots, and then we use roots to get rid of powers. There, I think I said it right the second time. So here, and again, it just depending on what the index to the root is to determine what power is, and vice versa. So here, these are going to cancel each other out. So x equals to 3 to the third power. That's 3 times 3, which is 9 times another 3 is 27. So x equals 27. So there's your answer. So the inverse of f at positive 2 equals 27. So this concludes the first part to inverse functions. I hope this video was helpful, but if you still have any questions, message me through Parent Square or message your instructor on My Open Math. But like always, I appreciate you watching, and I hope you have a great day.